Hi students, welcome to VEDA Gate Academy. Now, in the last session, you discussed about what means flat band diagram. Now I can able to go to discuss the MOS capacitor, and in that MOS capacitor, now I can able to examine different modes of capacitor for getting variable capacitance with applied gate voltage. Okay, students. Now I can able to go for what means MOS capacitor. So MOS capacitor you can able to examine. You know that in the case of a MOSFET, you already learned that according to the construction, the gate electrode and the conducting channel, separated by means of the oxidation layer of SiO2, you know students. So in the case of MOSFET, there is a separation between gate electrode and the conducting channel by means of this oxidation coating. So this structure look like to be a capacitor. So that capacitor should be called as what, sir? MOS capacitor you can call. And once again, what are the capacitance of that MOS capacitor can be varied by the applied gate voltage, students. So based on that, this MOSFET is also called as voltage controlled capacitor or voltage variable capacitor you can call. Confirm my option. So in the case of MOSFET, you know that there is a separation between gate electrode and the conducting channel by means of this oxidation of SiO2. So that structure look like a capacitor called MOS capacitor I told. And that body capacitance can be changing with the applied gate voltage. Based on that, the corresponding MOSFET can also be called as what, sir, means, right, voltage controlled or voltage variable capacitor you learn, students. Okay. Now, I can able to go for this MOS capacitor, students. So, depending on the type of substrate you may call, so you may find out two type of MOS capacitors. One is Nmos capacitor, students. Other one is a Pmos capacitor that you can able to examine. Confirm now? What I told, students? The separation of conducting channel and gate of polysilicon material, you know students, gate electrode by oxidation, that you know SiO2, students, look like a capacitor. Confirm. Called MOS capacitor, students. Look like a capacitor called what, sir? MOS capacitor. And this body capacitance can be changing with the applied gate voltage. Based on that, the MOSFET can also be called as a voltage controlled or voltage variable capacitor I can call. Confirm my option. The capacitance can be varied. The capacitance can be varied, students, with applied gate voltage you can call, with applied gate voltage, students, and thereby MOSFET is also called voltage variable capacitor. Confirm. Voltage variable capacitor I told. And this MOS capacitor is of two types, students. One is Nmos capacitor, other one is what, sir, means Pmos capacitor, students. So there are two type of capacitors we can call, right? So MOS capacitor is of two types, students. MOS capacitor is of two types you can call. So what are the two types of MOS capacitor, students? One is Nmos capacitor you can call, other one is Pmos capacitor you can call. Nmos capacitor. Okay. One more is Pmos capacitor, students. So there are two type of capacitors. Sir, structure of Nmos capacitor and Pmos capacitor both are same, just the type of substrate is different. A Nmos capacitor uses P-type substrate, students, whereas Pmos capacitor uses N-type substrate you can call. So Nmos capacitor uses P-type substrate, whereas Pmos capacitor uses what I can call N-type substrate I told. Confirm now, students? So Nmos capacitor uses P-type substrate Here Pmos capacitor uses n-type substrate, students. All remaining should be same. The structure of Nmos and Pmos capacitor should be same. Just they differed by means of the type of substrate you can call. In the case of Nmos, you may find out p-type substrate, students, whereas in Pmos you find out n-type substrate. Suppose now I can able to examine the Nmos capacitor, students. Now I can able to examine the Nmos capacitor. See this one now? Now I can able to go for the structure of Nmos capacitor, students. So you know that Nmos capacitor having a p-type substrate. So this is a p-type substrate, students. Okay. So this is a p-type substrate I can call. So Nmos capacitor uses a body of p-type substrate. So if I go for Pmos, in that place you can consider that n-type substrate. That's only a different, students. And from that substrate I take a terminal that to be called as a body terminal. So from that I take a terminal called body terminal, students. And this entire substrate is overlaid with what sir means oxidation coating. So this entire surface is overlaid with what sir means oxidation coating. You can call mostly prefer dry oxidation, students, already know. So that can able to form very, very thin layers. So this is a oxidation layer, students. So whose thickness is a T I can call very, very thin, students. And this is a oxidation coating who can act as a dielectric media. Students. Over which what will I do, students? Over which I can able to keep what sir means a polysilicon of P plus or N plus material that can act as another electrode or metallic plate you can call. So on this now introduced to keep what sir? A polysilicon of P plus or N plus, students. Polysilicon of P plus or N plus. So from that you take a terminal called gate terminal, students. Okay. So over this oxidation coating now I can able to introducing a polysilicon material, students, of either P plus or N plus you can call. So from that you can take electrode, students, that to be called as a gate electrode you can call. So this is the structure of Nmos capacitor. If I go for Pmos capacitor, A to Z is same. Only the thing that can be considered should be what sir means the type of substrate there if I use is what sir means n-type substrate you can call. Confirm now, students. Now across these terminals now I can apply a voltage for getting a variable capacitance. Confirm now. So that thing now I can apply here. This is that. So in between gate and body terminal you can apply the voltage for getting a variational capacitance, students. Sir, what is that variational capacitance? That I can able to examine by three different modes of operation. Students. So what I told you, Nmos capacitor having what, sir? Nmos capacitor has p-type substrate, you know, has p-type substrate, students, right? For which okay, thin oxidation SiO2, right, is kept, okay, and on which a polysilicon that can act as another electrode I can call polysilicon of P plus or N plus material is kept. Confirm? So over which a polysilicon of P plus or N plus material is going to be kept, you can call. Right. So depending on the voltage you apply, you find out what means. So different modes of operation. So it has three different modes of operation, students. It has three different modes of operation you can call. So what are the three different modes of operation, students? First one of that I can go accumulation. Okay. Next one of that one is what? Depletion. So accumulation mode, students. Next one is a depletion mode you can call. Final one is what, sir? Inversion mode. Final one is what, sir? Inversion mode you can call. And you remember that, students, this inversion mode should be appeared only in the low frequency mode of operation. While you can able to go for high frequency mode of operation, this inversion mode is not be possible. Confirm now? So you may find out three different modes of operation I can call. And once again you see this one now, students, this corresponding inversion mode, whatever that one I told here, that inversion mode is considered only in the low frequency operation. Whenever you can go for the same body in high frequency operation, the inversion mode is not possible. So now I can able to go to discuss in these three different modes. By that you can able to examine how the body have a variable capacitance. So first of that I can able to go for students the accumulation mode. So what is that accumulation mode that I can able to examine now? First of the mode I can able to go students, that to be called accumulation mode I say. Sir, what is accumulation mode, sir? Conditions for accumulation mode you see now. Sir, applied gate voltage should be here 0 or negative, sir. Here applied gate voltage should be Vc equal to 0 volt or negative, sir. So applied gate voltage should be either 0 or negative voltage, students. See, so now what happened there? Suppose I consider that negative voltage, students. If I apply negative voltage means, you observe now, this one negative, this is positive, students. Applied gate voltage is negative, you can call. This is negative, this is positive. Then according to the condition, you know that this surface may become what, sir? Negative charge, you know. That surface become what, sir? Negative charge, you can call. So this is the surface that become what, sir? Negative charge condition, you know, students. So here in this p-type substrate, which are the carriers are there? Who are the current carriers means holes, you know. Sir, that holes are get repelled by this positive potential there of the substrate material, and they are attracted towards this corresponding negative charge surface. That corresponding holes of this p-type substrate are attracted by what, sir, means this corresponding substrate and move towards the channel interface. So this is the place that to be called as a channel interface, students. That's be channel interface. So what are the holes of this p-type substrate that are going to be attracted towards this negative charge surface so that they can move towards what, sir, means this is channel interface, and they are accumulated there. They are accumulated there. They don't go to the other side, sir. Why, sir, means this is oxidation coating already know, which can act as a masking against the movement or diffusion of carriers. So what are the holes who try to move towards the channel interface? They can be accumulated or grouped or collected together. By that reason is called as the accumulation mode. That's that one, students. Can I draw that one now? Check up what I told. So accumulation mode I can call. So now I draw that structure, students, to you. So this is the body of p-type substrate, you know. Okay. So this is the terminal, body terminal. So you can find out that oxidation is there. This is the oxidation, students, of thickness T, you know. Okay. Over that, you know, polysilicon material of P plus or N plus, students. Polysilicon of P plus or N plus is there. Confirm now? This is a polysilicon material. So this is the gate terminal, students. Now what I told, sir, means that corresponding applied gate voltage should be what I told, sir. Negative I told. This is negative. This is positive I taken. So by that what I told, sir, this surface becomes a negative charge, you know. That surface becomes what, sir? Negative charge, students. So this is the negative charge surface. So what are the holes of this substrate are attracted towards this negative charge surface and move towards this channel interface. This is the place of channel interface you can call. That is the place of channel interface, sir. Confirm. So what are these holes who can move towards this channel interface? There they can be accumulated, grouped together like this. So this is called as accumulation of holes. Sir, that is the condition of accumulation of holes, sir. Sir, holes are free carriers are there. The accumulation of holes not causing any added barrier effect at the interface. Sir, barrier effect is considered by the ions, not by these free carriers. So even the holes are accumulated at the channel interface that do not causing any added barrier effect, sir. So in this corresponding accumulation mode, the body capacitance is considered just by the oxidation layer. So this is the oxidation layer. Only by that oxidation layer only we can able to get that corresponding body capacitance, sir. Here you don't find any what, sir, means the barrier effect by this accumulation of holes you can call. So the corresponding capacitance just considered by only the oxide region you can call. Confirm my option, students? Okay. Here what I told students, what are the holes of this p-type substrate, right? Confirm now. Holes of the p-type substrate are attracted by that negative charge surface and move towards the channel interface. Confirm? Move towards the channel interface, students, and accumulated at the interface of channel. They don't go to the other side, students. Why they don't go to the other side means because of what I told, oxidation coating. Because of oxidation coating, they don't go to that other side, students. Just they can come together and accumulate there. Sir, what is this accumulation of holes at the channel interface not causing any added barrier effect, I can call. So what is the accumulation of holes at the channel interface do not cause any added barrier effect, sir? The accumulation of holes at the channel interface do not cause any added barrier effect. Confirm? So do not cause any added barrier effect, students. So by this you can confirm here in this case what are the capacitance just considered by the only oxide region, not by the barrier condition. Confirm now? So in the accumulation mode, now finally you can confirm that the capacitance just considered by what, sir, means the oxidation region, sir. In accumulation mode, right, capacitance considered by what, sir? Oxidation region only, right? Who look like a dielectric of a body of capacitor. And what is that capacitance, sir? See this one now? C equal to COX, now I can call. That capacitance is called what, sir? Accumulation capacitance. C equal to COX stands for oxidation capacitance, sir. So right, that I can able to written like this. Epsilon OX by T. So this capacitance considered per unit area, sir. Unit is farad per meter square. Unit is farad per meter square, students. Where epsilon OX equal to epsilon or epsilon, students, permittivity of SiO2 you can call. It is a permittivity of what, sir? SiO2 oxidation. And epsilon, you know, that equal to relative permittivity of SiO2, sir. It is around 3.9 something. And epsilon already know, I think, permittivity of free space, that should be around 8.85 into 10 power minus 14 farad per centimeter, students. And what about that T, sir? T equal to already know gate oxide thickness. Gate oxide, that is what? SiO2 thickness, students. So it is what, sir, means gate oxide thickness, students. That is nothing but equal to SiO2 thickness we can call. And you know that gate oxide thickness will be very thin, and that as well as fixed one. So gate oxide thickness is a thin and a fixed one, sir. Thin means the capacitance is maximum, right? And as well as fixed one means capacitance is constant. Confirm my option, students, right? As T for gate oxide thickness is a thin as well as fixed, no change in the thickness, students. So that, okay, oxidation capacitance, whatever you can call, is maximum and constant. So in this region, I got that capacitance look like to be maximum and constant. That could be caused by only the what, sir, means the oxidation region you can call. Here no added barrier effect by the ions. Confirm now, students. So this is the first mode you can call, that to be called as the accumulation mode you can call. Now I can able to go for the next mode, students, that to be called as a depletion mode now. So what is that depletion mode I can able to examine? Second mode. Now I can able to go for the next mode of the operation, students, that to be called depletion mode. So what is this depletion mode, sir? Here you see this one now. The applied gate voltage should be greater than 0 volts, sir, and less than the threshold voltage. VT stands for threshold voltage, sir. The applied gate voltage should be greater than 0 volts, sir, and less than threshold voltage, so that VG look like to be small positive. It's not high positive, sir. It should be very small positive voltage you can call. So what I can call, sir, VG equal to very small positive. VG equal to small positive, sir. What happened here I can able to examine, students. So first one of that I can go. So this is your original figure. Now I can consider that a small positive, students. Now I can consider that what? Small positive I can call. So by applying a small positive voltage, what it is considered, sir? See this one now. This one become positive. This one become negative. So this surface become positive charge surface. Previously it is negative. Now it becomes a positive charge surface, students. That surface becomes what? Positive charge surface. So this is a negative surface you can call. Sir, previously all holes are here. Now what are that holes who are here, sir? In the previous case you said that all holes are accumulated here. So that holes can get depleted from that holes can get depleted from the interface, students. What are the holes who are accumulated in the previous condition that are get depleted? Depleted means moving away from the channel interface. Confirm my option. What are the holes who are considered to be accumulated in the accumulation mode that can get depleted? That can get what, sir? Depleted. That is nothing but moving away from the channel interface and move towards the subtrate by the attraction. What's my option? What are the holes who move towards the channel interface in the previous case? Now that can come to depleted from the channel interface, students, right? And they can move towards the substrate. So now according to the junction principle, whenever the pre-carriers left the junction or interface, according to the condition of junction principle, so the removal of holes can create negative ions. Suppose if it is electrons, the removal of electron can create a positive ions. That should be the junction principle condition, students. So this is the interface you can call. So at the interface, the removal of positive carriers can able to generate negative ions. The removal of negative carriers can generate positive ions. Who can left out from the interface, sir? Holes are left out from the interface. The removal of these holes or the interface can able to cause up the growth of negative ions. Confirm my option. Check out this. Just to indicate this one, students. So what are the holes you can call that can get depleted now, right? That can get depleted, sir. Instead of moving like that, that holes can move like this now. And so now, so the removal of holes from the interface can able to cause up what, sir, means the growth of negative ions, right? This is the interface. That is nothing but the barrier effect condition, students. So there you can get the negative ions like this. Why the negative ions, sir? Because there the carriers that are left out from the interface is nothing but the holes. The removal of that holes can able to generating negative ions that can causing a barrier effect you can call. So you may get a barrier effect by the addition of this negative ions. So at the channel interface, you may consider that two type of media. One media is nothing but oxidation, another media is nothing but what's a barrier. So here the capacitance is considered by both oxidation region and barrier. That's a condition, students. So by that it is called as a depletion. Depletion means making the carriers to deplete from the surface. So the depletion of the carriers from channel interface can able to cause up the growth of negative ions according to the channel interface principle you can call. Whenever the carriers left out from the junction place, the removal of that carriers can able to cause up what, sir, means ions. The removal of holes can able to cause up negative ions. The removal of electrons cause up positive ions. Okay, check out this one now, students. So depletion mode I can call small positive, sir. This is the structure, you know. I redraw that one now. Okay. This is the P-type substrate, you know. So terminal of body. Okay. So oxidation coating. Thickness is a T, you know. Right, sir? So polysilicon material, you know. P plus or N plus, students. Okay, this is the gate, you know. This is the body terminal. You are applying a small positive voltage, students. You are applying a small positive voltage you can call. This is a small positive, students. By that, this surface is positively charged. what are the holes who are accumulated at the channel interface in the previous case? So this is the channel interface, students. So this will be the channel interface you can call. Interface of channel, So from that channel interface by this one, so by this attraction, the holes are depleted now. This is called depletion of holes. Depletion of what are holes? Depletion means they can move away from the interface. What are the depletion of holes from the channel interface can able to cause up what are means negative ions, growth of negative ions like this. So you are getting added barrier effect by the negative ion, students, like this. Okay, I assume that the width of this barrier should be D, can call. That barrier effect width equal to D, can call. So what is this one, sir? This should be added barrier effect, you can call. Added barrier effect by what? Negative ions at the interface. So that the capacitance is considered by both oxide region and barrier in this case. Confirm my option, students. So what I told you here with the small positive gate voltage you can call. In this case, what I told students, by attraction, the holes can be depleted. Confirm. Depleted means moving away, students, from the channel interface, you say. So can be depleted from the channel interface, students. Okay. So can be depleted from the channel interface and move towards what? The substrate. Move towards the substrate terminal, nothing but body terminal you can call. Confirm. So what I told is, sir, the depletion of holes at the interface causes a added barrier effect, I call added barrier effect, students, by negative ions. Added barrier effect by negative ions you can call. Confirm my option. Removal of holes at the interface can able to causing added barrier effect by negative ions you can call. So as a result, what I told, sir, the capacitance is considered by both what sir means oxide region and what you can call, sir, what that one means added barrier effect you can call. This is the case. See this one now. So both are side by side, students, like this you can call. This is the capacitance considered by the oxide region you can call, to which the added barrier effect is there side by side adjoining position. So this is the capacitance considered by the barrier. So the resultant capacitance considered by both COX and CD, students, where COX is the capacitance considered by the oxidation region, CD is the capacitance considered by the added barrier, students. Okay. So now you can able to examine the capacitance is considered by both oxidation region and by added barrier effect. So both things considered, sir. The capacitance is considered by both oxidation region and what, sir? Added barrier you can call. So what that capacitance, sir? That capacitance now I can written like this, students. They are side by side you can call. So the total capacitance C equal to, like this, capacitors in series equal to resistors in parallel, C equal to COX CD by COX plus CD. C equal to COX CD by COX plus CD, students. What is that COX, sir? Where COX, students, where COX is what, sir? COX equal to oscillation capacitance, where COX equal to epsilon OX by T, students, already you learned this. Unit is farad per meter square. That to be called oxidation capacitance. Confirm. And what is that CD, students? CD equal to barrier capacitance. Sir, that barrier is formed in the substrate. Substrate is a body of silicon. Confirm my option. Sir, where the barrier is formed, sir? Barrier is formed at the channel interface in the substrate body. Substrate body is purely a body of silicon. So that is a permittivity of silicon, sir. Epsilon SI I can call like this. So what is that barrier width, sir? I indicate in the diagram. D can call. D stands for width of the barrier, sir. Again, it is also considered per unit area, farad per meter square. That to be called barrier capacitance. This is barrier capacitance, sir. Where again, epsilon SI equal to epsilon R, epsilon naught you can call. So permittivity of SI, sir, not SiO2 here. It is a permittivity of silicon. And epsilon R equal to here, relative permittivity of silicon. That equal to dielectric constant of silicon. What is this relative permittivity of silicon, sir? It is around 11.7, sir. Roughly you can call 12. And what is the width of the D, sir? D equal to width of the barrier you can call. D equal to what, sir? Width of the barrier you say. Sir, in this region, as increasing the voltage in between that range, what is that one, sir? Barrier effect is increasing there. Then the resultant capacitance comes to decreasing, sir. And thereby that capacitance may become minimum. Confirm my option, sir. What I told here. Sir, increasing of the voltage in this range, so barrier size increases, right, depending on the applied voltage you consider in that range. So automatically the resultant capacitance comes to decreasing, and there is a chance to maintain that capacitance should be minimum. Sir, in the previous case I told capacitance is look like to be maximum and constant. Now that capacitance becomes what, sir, means decreasing and become minimum here. Confirm my option, sir. So here the capacitance decreases and becomes what? Minimum you can call. Can I write now? The capacitance decreases, sir. The capacitance decreases here as we increasing the voltage in between of 0 and what, sir, means VT you can call. The capacitance comes to decreasing, sir, and become minimum. You know that capacitors in series as same as resistors in parallel, so that when the capacitors are connected in series, the total capacitance comes to decreasing. So and look, let it become minimum in the depletion mode. So this one is the second mode, sir. First mode, capacitance look like maximum and constant, where the capacitance considered only by oxidation. In second mode of depletion, the capacitance is considered by both oxidation and what, sir, means added barrier, and the resultant capacitance in this case decreasing and become what, sir, minimum you can call. Now I can able to examine the other mode, sir. That is called inversion mode. Now third one I go. Inversion mode, students. Third mode of this, I can able to go inversion mode, you say. What is this inversion mode, sir? Here, applied gate voltage should be greater than or equal to VT. VT stands for threshold voltage. Applied gate voltage should be greater than or equal to VT, sir. So, applied gate voltage is more positive. That is, Vc equal to more positive, sir. And that voltage is enough to break the covalent bonds on the substrate of corresponding that corresponding p-type material you can call. That's my option, students. Here applied gate voltage is enough to break the covalent bonds, because applied gate voltage should be greater than VT, sir, and it have a chance to create the inversion layer. What that one? I can show that one to you, students. First diagram I can go. So this is that one, okay. Sorry. So original figure I come back, students. So this is the depletion mode. Carriers are depleted, you can call. Now I can able to go for inversion mode, sir. Here applied gate voltage is enough one. I told it is enough one. What, sir, means to break the covalent bonds on that substrate I told. What happens, sir, here? You observe now the covalent bonds are get broken here. With the applied gate voltage, the covalent bonds are broken, sir, on that p-type body of substrate. The breakage of covalent bond give up what, sir, means additional carriers of electrons and holes. You know already. Electrons and holes are generated. And it is nothing but a more positive, sir. What are the holes who are that generated there? That holes can able to move towards the substrate by the attraction. And what are the negative carriers of electrons that can able to move towards the interface like this? And these electrons can able to occupy the place of channel interface now. the breakage of covalent bonds can give up electron hole pairs you can call, and among that holes can able to move towards the substrate body terminal, and the electrons can move towards the interface, and there they can be accumulated along with the added negative ions. Already you know that negative ions are there. Along with that one now, the electrons also occupy that place. Sir, remember now, the barrier effect is considered as long as in that area none of the free carrier is there. Confirm my option? So, if none of the free carrier is there, you may consider that barrier effect by that ions. Sir, once in that area free carriers are considered, the barrier effect comes to reduces. Confirm my option? So, by the breakage of covalent bond, electron hole pairs are generated. Among that, holes can move towards the substrate terminal, but electrons are moved towards the interface, and there they can be accumulated at the interface. The accumulation of these negative electrons at the interface forms an inversion layer. So, inversion layer is what, sir, here? It is the process of generation of opposite charge carriers. It is the process of generation of opposite charge carrier at the channel interface to reduce the effect of the added barrier. To reduce the effect of the added barrier. Sir, it is a p-type body. This is the opposite charge carriers of electrons. So, that is layer is called as the inversion layer, sir. It is the process of generation of opposite charge carriers at the interface to reduce the effect of this, what sir means, negative ions. So that on the accumulation of this negative electrons at the interface, the added barrier effect by negative ions slowly reduces. So as it slowly reduces means, then the barrier capacitance, what you can call, that can come to decreasing. So the barrier capacitance comes to decreasing means, then the resultant capacitance goes to be increases. The total capacitance, you know, in the previous case, what is that one? So considered by COX and CD. As the CD come to decreasing, you can call, then the total capacitance comes to decreasing, sir. Comes to increasing, sir. Total capacitance comes to increasing, right? And once again, whenever you can able to go for a strong inversion, sir, whenever you can able to go for strong inversion, sir, where this added barrier effect is completely nullified. Added barrier effect is completely nullified in the strong inversion area. So there you find out that the capacitance again by only the oxidation, not by the barrier. Confirm my option? So increasing the gate voltage above the threshold. So there is a successive breakage of the covalent bonds on that substrate you can call. Additional electron hole pairs are created, I told. In that holes can able to move towards the substrate terminal, sir. What are the electrons can able to move towards the interface? Karmana? And they can be accumulated at the interface, and this accumulation of electrons at the interface forms a inversion layer. So inversion layer is the phenomenon of generation of opposite polarity charge carriers at the interface to cancel or reduce the added barrier effect. So as the barrier effect comes to reducing, then the resultant capacitance increasing. So once the inversion layer becomes stronger, under that condition, the added barrier effect is completely nullified. Once the barrier effect is completely nullified, sir, the capacitance again be considered by only oxide region, such that capacitance again become maximum constant like accumulation mode, sir. That's the inversion mode you can call. Come on, students, I can go for that. Just can able to clear this. So we can able to redraw that figure in accumulation mode, sorry, in inversion mode. Students, now I can come back to that inversion mode now. Okay, so now I can able to examine that, students, inversion mode now. Check up the inversion mode condition. So inversion mode is nothing but Vc equal to more positive, students. Now I can draw that one. See this one now. So this is the body of p-type substrate, students. This is the body terminal, students. Okay, now I can able to go for oxidation, students. This is the oxidation. So this is SiO2, students, whose thickness is a T, you know. Okay, over that you know that polysilicon thin material is there. This is a polysilicon of P plus or N plus, you know. 8. So I applied is a more positive voltage you can apply. Confirm. This is the interface of channel. So previously in the depletion mode you find out there what sir means added barrier effect by negative ions you can call. added barrier effect by negative ion students. Previously, no. Okay, this is the added barrier effect, students. Now I can able to go forward, sir, means the inversion mode I can call. I can able to go for the inversion mode, students. In this inversion mode, what I told, sir, there is a breakage of covalent bonds. There is a breakage of covalent bonds on this substrate body. The breakage of covalent bonds can give up what, sir? Electrons and holes, students. Electrons and holes. Among that, the holes can able to move towards the substrate terminal. Confirm? And whatever the electrons who are generated there, that can able to go forward, sir, means towards the channel interface like this. So towards the channel interface they can able to move, and accumulated there I can call, and they can able to go to be accumulated at the channel interface. So students, they are the persons that can be accumulated at the channel interface, you can call like this. So as long as no free carriers is there, the ions effect you consider. Once that free carriers are occupied in that area, the ions effect comes to reducing, the barrier effect comes to reducing, sir. And what is this one, sir, means? So this layer is called as the inversion region. So the function of this inversion region is to reduce the added barrier effect, you can call. Slowly the capacitance increasing, and once the inversion layer becomes stronger, that added barrier effect becomes zero, such that capacitance just considered by the oxidation region, like what, sir? Your accumulation mode, you can call. That's a condition, students. Okay. Now you can able to examine what it's. So Vc greater than equal to Vt, Vc equal to more positive, students. So in this, so what I told, covalent bonds, okay, in the substrate body can break up, you say, confirm, and generate additional electron hole pairs. Confirm. Additional electron hole pairs, and in this the holes can move towards, confirm, substrate terminal, students. Move towards substrate terminal, whereas electrons move towards interface. Electrons move towards interface and accumulated there. Interface and accumulated there, sorry. And accumulated there, students. So there they can get accumulated, students. So the accumulation of opposite polarity carriers that can form what's that means inversion layer, right? Which causes an inversion layer, I told. Which causes an inversion layer, sir. What is that inversion layer I told to you, students? The function of the inversion layer. So, inversion layer is the phenomenon of generation of, okay, opposite polarity charge carriers at the interface. Okay, at the interface you can call. Sir, what is the function of the inversion layer, you know? The function of inversion layer is to reduce the added barrier effect. So reduce the added barrier effect, sir. so that depletion capacitance decreasing and total capacitance increases, sir. Right? So that depletion capacitance decreases and total capacitance comes to increasing, sir. So whenever you can able to go for strong inversion layer, the complete barrier effect is cancelled and the capacitance is considered by the oxidation region, which look like to be maximum and constant, you can call, students, right? In the strong inversion region, okay, barrier effect is completely removed, right? So that no depletion capacitance, sir, CD equal to 0 and total capacitance C equal to C oxidation. Total capacitance C becomes only C oxidation, sir, not that barrier capacitance, that is 0, right? Which equal to what, sir, again? Maximum and constant, which is again maximum and constant, sir. So this would be called as a inversion mode, you can call. This is the thing what, sir, means inversion mode, you can call. Confirm, understood, students? First I discuss accumulation mode, applied gate voltage 0 or negative. So there the accumulation of free carriers at the interface not causing any barrier effect, you can call. Anyhow there the capacitance look like to be only by the corresponding oxidation region, which is thin and fixed one, so that capacitance maximum and constant. Next, apply a small positive gate voltage that can able to deplete the free carriers from interface towards the substrate, and thereby that can cause up some barrier effect at the interface. So their capacitance is considered by both oxide and barrier. So the resultant capacitance decreasing and become minimum, I told. And again I can go for inversion mode with applied gate voltage above threshold voltage. What the thing you may find out here, sir? So the barrier effect come to decreasing with the effect of the inversion mode or inversion region at the interface, so that the capacitance increasing. Once I can go for a strong inversion mode, there the barrier effect condition is completely vanished out, so that no capacitance by the barrier, only capacitance considered by oxidation, which is considered to be maximum and constant. So I can show that one, all these things, students, by means of a graph. So capacitance versus voltage characteristic graph I can show. See this one? So this is the CV characteristic graph, students. What are the thing I told that I can able to examine to you? This is the capacitance of the body, students. This is the applied gate voltage, plus Vc minus Vc. This is for Nmos capacitor, students. This is for Nmos capacitor, I can call. Okay. Now let us see this one now, what I discussed, sir. First, for 0 or negative, it is in accumulation mode, where the capacitance is maximum and constant. This is that. So this, the capacitance is maximum and constant, sir, considered by only COX. Only COX, you can call capacitance is maximum and constant. Thereafter, once you can able to go for a depletion mode, the capacitance decreases and become minimum. The capacitance decreases and become minimum, you can call. This is the case, students. So this is the particular voltage called threshold voltage. So that is a weak inversion. Now the inversion starts now. By that it is called as a weak inversion area, sir. Whatever the threshold, that is called as a weak inversion area. So once that inversion region formed, then the capacitance, what, sir, means the effect of the barrier capacitance decreases, then the resultant capacitance increases, I told, students. And once you can able to go for strong inversion, the capacitance again become maximum to constant. So this area is called as a strong inversion. Here again the capacitance is just considered by what, sir, means COX. Confirm, students. And here you know that the capacitance is considered by what? This area, the capacitance is considered by what, sir? C equal to COX CD by COX plus CD, no? Confirm now? This is the capacitance decreasing, where capacitance considered by both oxidation region and barrier. And you know that one, sir, this area is called accumulation, students. This area called accumulation. Confirm? And what is this one, sir? This is the area called what, sir, means depletion, you say. So this is the area called depletion, students. And this is the area to be called what, sir? Inversion, you say. So at VT it can start with weak inversion and it goes to be increasing. Once that completely barrier effect cancelled, there you can find out a strong inversion, so that the capacitance is considered just only by oxidation region. And all this is the thing concerned in the low frequency region, students, in the LF region. LF means low frequency region, sir. Same MOS capacitor, if I go to operate in the high frequency region, what you can call, sir, the graph structure is the same. Small change you may find out, this inversion mode not be appeared. This inversion mode not be appeared. Why, sir? In the inversion region, sir, in the high frequency region, inversion mode is not possible there. What are the problems, sir? Means in the high frequency region, the barrier is effective. So the barrier is effective such that the capacitance look like be maximum, sir, the capacitance look like be minimum and constant there. So the barrier effect is not be cancelled. In high frequency region, the barrier is effective, sir, such that inversion mode is not possible. Inversion mode is what? Not possible, sir. Same graph now I can able to examine. Says for now. What I told? In HF region, I say. HF means high frequency region, sir. So, inversion mode is not possible, I told. Is not possible, sir. As barrier is effective at high frequency model. So it should not be vanished there. In high frequency model, barrier is effective, sir, which is not be vanished there. So that inversion is not be possible, sir. If I draw that graph, sir, what that graph may come, so I can show that again here. See this one now, students. This is capacitance. Same for Nmos, I can read that given. So this is valid for low frequency. Now I can able to go for high frequency, students. So no change in accumulation mode, it should be same. There the capacitance considered by only COX. So this is the depletion mode, students. So this is the threshold value you can call. That is a weak inversion, just you told there here. But here the inversion not be possible, students. So what is that one? Once it reach minimum, there it look like be maximum and constant. Sorry, there it look like be minimum and constant, students, as it is. No change in that. This is the case. Like this. So here the capacitance is considered by what? Sir, capacitance considered by COX and CD. That is COX CD by COX plus CD. So no inversion mode, students. This entire thing look like be what, sir? Inversion or depletion mode only. So this is the accumulation you can call. So it is what, sir, means depletion mode. Inversion mode not possible, sir. Depletion mode only. Capacitance once reach the minimum, there the capacitance look like being minimum and constant, no further change. Same Nmos capacitor graph, sir. Okay, this is again Nmos capacitor in high frequency region. So as compared to low frequency region, the small change you may find out what, sir. So what is that inversion mode I told there? That inversion mode not be appeared here. That's a Nmos capacitor capacitance versus voltage characteristics. If you want, you can also draw the characteristic graph for Pmos. Just I draw that graphs to you. Pmos capacitor graph also I can do that one, students. Check up now. Both low frequency, high frequency. So graph nature is same, just axis is reverse. Okay. Minus VZ I call, plus VZ. This is the capacitance. So you may find out the for positive VZ it is in accumulation mode, sir. Reverse. For Pmos it is the case, sir. This is the accumulation mode you can call, where the capacitance just considered by COX. Okay. And the capacitance are decreasing, students. So this is VT, for Pmos, what you can call VT negative, sir. And once again, that corresponding inversion layer starts, sir. Thereby the capacitance increases and become maximum in the strong inversion region. This is that. So here the capacitance is considered by what both oxidation and barrier, sir. COX CD by COX plus CD, students. And here the capacitance is only by COX, that is a strong inversion you can call. It is what, sir? Strong inversion, you say. Strong inversion, students, it is. So this area is a strong inversion, you can call. Confirm? Sir, what is this one, sir? It is a low frequency model, sir. This is the accumulation, you can call. So this is the what, sir? Depletion, you can call. And this one is what, sir? Inversion, you can call. So this is the Pmos capacitor graph in low frequency region, sir. Pmos capacitor graph in low frequency region, you can call. Maximum constant, oxidation capacitance. Capacitance are decreasing, become minimum. So this is the weak inversion area, sir. And again, it can go to be increasing, and that becomes as what, sir? Maximum constant. There it is called as a strong inversion, where barrier effect become cancelled. Okay. Same Pmos capacitor in high frequency model, like this, sir. Same Pmos capacitor in high frequency model I can able to do. This is the Pmos capacitor in high frequency model, sir. Capacitance, this one. Confirm on these things. Now we can able to examine what it is. So this is the accumulation mode, sir. You know that COX. There the capacitance considered only the oxidation region, that is maximum and constant. No change in that, even in high frequency model. Next, what you can call, sir, a depletion mode, no change, and come to minimum at VT I can call. And after that, inversion mode is not possible here because the barrier is effective at high frequency, so that the capacitance look like be what, sir, means minimum and constant like this. No change in that. So no inversion mode you may find out here, sir. So what you can call, sir, this will be the accumulation mode. And this will be the depletion. So here the capacitance come to what? By both oxidation and barrier. So that the barrier should be effective at a high frequency such that capacitance become minimum and constant. So this is the same Pmos capacitor in high frequency model, sir. Pmos capacitor in high frequency region. Confirm, sir. So this is the graph for Pmos capacitor, capacitance versus voltage. And so this, students, this is about the MOS capacitor. Now I can able to examine some practice questions, students. Okay, check out the question now. So one of the question I go, students. The Nmos circuit is shown having mu n COX, that is, transconductance parameter, students, equal to 100 microampere per volt square. VT threshold voltage equal to 500 millivolt. And channel length modulation lambda equal to 0. What is the value of V0? Right, V0 asking, sir. Options 0.5 volt, 0.6 volt, 0.4 volt, 0.1 volt. So now I can able to check up this is the diagram, students. What is the thing given? So just I redraw the diagram here for easy to you. This is the diagram given. This is a Nmos capacitor, sir, Nmos transistor. Okay, so aspect ratio indicated here as a W by L, that is a 10. So gate and drain are shorted, students. This is the place of V0 you can call. And this in this place drain current source is given, that is a 5 microampere, that is itself a drain current. And that concerned supply is given, sir, 2 volts. What that V0 is asking? Sir, you know that this is gate, source, drain. Already you learned that, students, gate and drain are shorted so that the bodies are directly in saturation mode. As gate and drain are shorted, the body is in saturation mode, students. So this is the drain current, Okay. So ID equal to how much? 5 microampere you can call. Mu n COX is given. Transconductance parameter 100 microampere per volt square. Okay. Lambda 0. Threshold voltage 500 millivolt means 0.5 volts, sir. Confirm? And what is the thing you can call, sir? Aspect ratio is given 10, sir. If you observe this diagram, gate and drain are shorted, sir. Gate and drain are shorted. Okay, that is gate potential is equal to drain potential, sir. So that VGS equal to VDS. VGS equal to VDS, students. That should be equal to V0 here. So as VGS equal to VDS means, and it is in saturation mode. Confirm? You asking output V0, sir, there. It is in saturation mode, students. What is the equation of drain current under saturation mode? You can come back. So this is the formula, you know. ID equal to mu n Cyx W by 2L into VGS minus VT whole square. This is the thing, students. Now I can substitute everything there. ID is 5 micro. Okay. Mu n Cyx is 100 micro, students. W by L is a 10 by 2 as T is. VGS equal to VDS, that equal to V0 I written. VT equal to 0.5 whole square. So by that you can able to get the value of V0, students. Check up now. So 10 power minus 6, 10 power minus 6 out. 100 by 2, sir. So that is another but what sir means 500 you can call. So this is another but what you can call, sir, 5000 is there. 5 equal to. So this is another but sir means 500 you can call into V0 minus 0.5 whole square. Okay. Take this one this side, sir. 5 by 500 become 1 by 100, students. 1 by 100. Okay. 1 by 100 equal to V0 minus 0.5 whole square. V0 minus 0.5 whole square, students. 1 by 100 equal to what, sir? Point. That is nothing but what, sir? Remove the square root there, square there. 1 by, that is nothing but 1 by 10. 1 by 10 become 0.1, students. V0 minus 0.5. Okay. So 0.1 equal to V0 minus 0.5, students. Then what about V0, sir? V0 equal to 0.6 volt. 0.5 plus 1, sir. That is 0.6 volt you can call. That becomes a 0.6 volt, sir. 0.1 plus 0.5 plus 0.1, sir, that equal to 0.6 volt. Sir, if I do the square root, that is nothing but plus or minus 0.1, sir, then only why do you take 0.1? Means suppose if I take minus 0.1, sir, that become 0.4 volt here. So whenever VDS equal to, what you can call? 0.4 volt, what it happens, sir? You check up there. If V0 equal to VDS, that equal to 0.4 volt is there, it should be less than VT, sir. If it's less than VT. So whenever it is less than VT, it is look like an off state you can call. It look like what, sir? Off state. So that minus 0.1 I don't taken. Understood my option what I told? Sir, you taken that to remove the square root, it becomes is another but here. Root of that one means plus or minus 0.1 you take. Why do you write just only 0.1 means? Suppose if I write plus or minus 0.1, sir, that is nothing but one case is 0.6, other case is 0.4 you may get. Suppose if I use 0.4, sir, what that one means? VDS equal to VGS, that equal to 0.4 there. Then VGS look like be less than VT. VDS less than VT means the body is in off state, not been on state. So that corresponding 0.4 volt is not applicable. Confirm my option. So if I take that it is plus or minus 0.1, that become as a what, sir? 0.6 or 0.4 volt. Suppose if we take 0.4 volt, the corresponding V0 same as VGS, that look like be less than VT of the threshold you can call, such that the body is not been conducting mode. That completely so indicate that wrong condition of your statement. So already you learn saturation mode. So that should be a false at that time. So output V0 0.4 volt not allowed. Only the thing is nothing but 0.6 volts, sir. Okay. What is the option for this? B, sir. B is the answer for that. Okay. Check out the next question now. A NMOS operating at VOV. VOV means overdrive gate voltage. Right? 0.5 volt. Exhibit a linear resistance already equal to 1 kilo ohm. Linear resistance already equal to 1 kilo ohm. When VDS is very small. Right? When VDS is very small. Applied drain voltage is small. That is a linear reason, you know. So what is the value of ID? What is the value of drain current ID when VDS is increased to 0.5 volt? What is the value of ID when VDS is increased to 0.5 volt? You can call. So options is given 0.5 milliampere, 0.125 milliampere, 0.25 milliampere, 0.6 milliampere, students. So now what is the thing you can call? VOV given, that equal to VGS minus VT, sir. Overdrive gate voltage it is. That equal to 0.5 volt. Confirm? So linear resistance or drain resistance is given already equal to dou VDS by dou ID, students. in 1 kilo ohm when VDS equal to small. Okay. Sir, commonly you know that what you asking sir means what is the value of ID? Okay, at VDS equal to 0.5 volt. This is the thing he asking. Sir, whenever VDS equal to 0.5 volt, that equal to VGS minus VT, then the body may enter the saturation mode. Under saturation mode, what is the equation of drain current? You know, K into VGS minus VT whole square. K into VGS minus VT whole square, sir. So VDS equal to VGS minus VT, thereby you can able to apply that one, no problem. But the unknown thing is there. What is that one, sir? K not be given, sir. Transconductance parameter not be given. I can able to calculate that transconductance parameter using this what's the means of drain resistance. So when VDS is small, drain resistance is given, and you know that whenever VDS is small, the body is in the linear mode. Kanbana, check up my option. Step 1 I go, sir. When VDS is small, it is in linear mode. Then what are the equation of drain current there? The equation of drain current like this, sir. ID equal to K dash into VGS minus VT into VDS minus of VDS square ampere. So this is the drain current you can get, students. Now I need that to dou VDS by dou ID. So first I can do that to dou ID by dou VDS. After that I take a reciprocal. So by that I can get the transconductance parameter with the drain resistance given, students. Okay. Now I can able to go forward, sir. Dou ID by dou VDS first. Dou ID by dou VDS I can do, students. So K dash constant take out as it is. So now I do the differentiation with respect to VDS means. So VGS minus VT is a constant, students. First you write down that one as it is. VGS minus VT are written as it is. So differentiation of VDS with respect to VDS is 1. Differentiation of VDS with respect to VDS is 1, students. Right? Next, minus 1 by 2. Differentiation of VDS square with respect to VDS means into 2 VDS, students. So 2 cancelled out there. 2 become cancelled out. Then what it comes here? K dash into, right, VGS minus VT minus VDS you can call. This is the thing. Already given VDS is a small, students. So it is approximately equal to like this. K dash into VGS minus VT, since VDS is negligible or small, you can call. So that it should be less as compared to VGS minus VT. Okay. So now I can able to go for what's a RD equal to dou VDS by dou ID, that equal to 1 by K dash into VGS minus VT. Confirm? Okay. Now I can able to go for what's our K dash now? K dash equal to 1 by RD into VGS minus VT. So I transfer K dash here, 1 by RD into VGS minus VT, sir. I substitute those things to get K dash first. So K dash equal to 1 by RD into VGS minus VT can call. So RD is how much is given, sir? RD is 1 kilo ohm and VGS minus VT equal to 0.5, students. Okay, this is 1K. This is VGS minus VT given 0.5, students. 1 by 0.5 become 2, students. 2 milliampere per volt square. Unit for K dash, you know. So that becomes as a 2 milliampere per volt square now. So first step out, I calculate the transconductance parameter. Next step, I come back. What are you asking, sir? ID is asking at VDS equal to 0.5 volt. Okay. So as VDS equal to 0.5 volt, which is equal to VGS minus VT now. So that is VDS equal to VGS minus VT, you say it is in saturation. So body go for saturation mode, sir. The body can go for what, sir? Saturation mode you can call. What is the current in saturation mode, sir? ID equal to K into VGS minus VT whole square ampere. But here is given K dash, sir. So K equal to K dash by 2, you know. K dash by 2 into VGS minus VT whole square ampere. Substitute K dash there. So ID equal to K dash is what, sir? 2 milli, 2 into 10 power minus 3 by 2 into VGS minus VT, sir. VGS minus VT, how much is there? That you already know, 0.5, sir. 0.5 whole square ampere. So 2 out. So 0.5 whole square become 0.25, sir. 10 power minus 3 means milliampere. So the resultant drain current at VDS equal to 0.5 becomes 0.25 milliampere, sir. 0.25 milliampere. What the answer? Check out that. See, sir, answer 0.25 milliampere. Okay. I can able to examine, sir. Third one. In the figure given, modulus of ET equal to 0.4 volts, sir. Threshold voltage. What the state of M1 and M2 respectively are? What the state of M1 and M2 respectively are? So these are the two MOSFET transistors is given. What the state of each of that one I am asking. So options given: saturation, saturation, linear saturation, saturation, linear, linear, linear. Now I can able to redraw that circuit, students. Check up this. What are the thing given? Two MOSFETs are given. Both are Pmos, students. So first one I can go. This is the first one of that. Okay. So gate terminal is connected to 0.5 volt supply. So it is grounded, sir. This is the source connected to 1.5 volt supply, students. So that should be grounded. Drain should be connected to ground, students. This is the drain that is connected to ground. This is M1. So what is the mode of that one? He asking, sir. Now I can able to check out everything of this. So modulus of ET equal to 1 volt, sir, there. So for Pmos, sir, it is not Nmos. This is for Pmos user. Now I can able to examine the Pmos of that one, students. What is that one I can able to go? That is M1 you can call. So yes, for now, what is that VSG, sir? Vs minus Vz. Vs equal to 1.5. Vz equal to 0.5. That equal to 1 volt. And VSG minus modulus of Vt, sir. That is 1. Modulus of Vt is 0.4. That become 0.6. Okay. Now I can able to go for VSD, students. VSD. Source potential is 1.5. Drain potential 0. That is 1.5. If I compare VSD with VSG minus VT of overdrive gate voltage, VSD is greater. As VSD greater than VSG minus modulus of VT, so it is in saturation. So M1 is out, it is in saturation, sir. Come back to M2, sir. Now I can draw that circuit diagram here. I can indicate that one, students, here. This is M2. Source, drain, gate. So gate is directly grounded, sir. Drain is connected to what? 0.9 volt supply, students. This is connected to 0.9 volt supply. And this one is connected to what, sir? 0.9 volt again. This is M2, sir. Okay, this is for Pmos of M1 you can call. This is for Pmos of what, sir? M1. Now I can able to go for, sir, for Pmos of M2. Second one for Pmos of M2, students. For Pmos of M2, now I can able to go. What is that VSG, sir? VSG equal to Vs minus Vz. Vs is 0.9, Vz is 0, sir. 0.9 minus 0, that equal to 0.9 volt. And VSG minus modulus of ET, students, 0.9 modulus of ET is 0.4, that become 0.5 volt. Confirm. Now I go for VSD, students. VS minus VD. VS is 0.9, VD is 0.9 again. So that is 0.9 minus 0.9, students, that equal to 0 volt. If I compare both of that, you see this one now as VSD comparatively less than VSG minus modulus of VT. It is 0, that is 0.5. So this fellow is in linear region. So first one of that one is in saturation, sir. Second one of that one is in linear. So option is what, sir? Linear, saturation and linear. So option is C. So M1 is in saturation, M2 is in linear region, students. Remember now? Check out the next question now. A NMOS operate at ID equal to 0.4 milliampere. A NMOS operate at ID equal to 0.4 milliampere and VD equal to 0.5 volt. It has a threshold voltage 0.7 volt. Mu n COX equal to 100 microampere per volt square. W equal to 32 micrometer. W equal to 32 micrometer. L equal to 1 micrometer. Assume lambda equal to 0. Calculate the values of RS and RD, biasing resistors. RS and RD respectively are 3.25 kilo ohms, 5 kilo ohms, 7 kilo ohms, 5 kilo ohms, 4 kilo ohms, 3.25 kilo ohm, 2.8 kilo ohm, 3.25 kilo ohms, students. So this is the circuit given. I redraw that one to you. Check up this. This is NMOS circuit, sir. Okay. So this is the node of RS containing supply is minus 2.5. So node potential is VS equal. So this is a drain node potential. Here this is RD, students. This is 2.5 volt. Okay. This is what, sir? Grounded. Gate, source, drain. Sir, in that what he given, sir? Check out what the thing is given. So ID is given, sir, 0.4 milliampere. ID given 0.4 milliampere and VD is given, sir, 0.5 volt. Drain potential is given. So VT is 0.7, sir. Threshold voltage is 0.7 volt. And transconductance parameter mu n COX equal to 100 microampere per volt square. Channel width is 32 micrometer. Okay. Channel length is 1 micrometer. Lambda 0, sir. What is asking? RS and RD. RS and RD is asking, students. So one of that I can directly calculate here. RD is directly calculated, students. Here which current flows? Drain current can flow. There the drain current can flow, students. RD can directly calculate it. What? 2.5 minus VD by ID. 2.5 minus VD is already given 0.5, students. There. So already given that one. So that is nothing but what you can call, sir. Directly can get RD. So first anyhow I can calculate RS. And after that you can directly calculate RD, sir. Check up now. How to calculate RS, sir? So RS equal to what you can call VS minus of what, sir, means minus of minus 2.5 by corresponding ID you can call. ID, you need to know this source potential, students. You need to know that source potential automatically may get that corresponding resistance RS. Now I can able to go forward, sir, means what is the gate potential here? 0. Drain potential is what? 0.5 volt. Confirm now? See this? Gate voltage directly grounded 0 and drain potential is what, sir? 0.5 volt. Then VD greater than VZ or VDS must be greater than VGS. So keeping VDS greater than VGS, sir, it is a chance to operate in linear saturation region, sir. It is in saturation. Sir, what is the condition under saturation? This is the formula of drain current. ID equal to mu n COX W by 2L into VGS minus VT whole square. So this is the formula for drain current, students. ID equal to mu n COX W by 2L into VGS minus VT whole square you can call. So now I can able to substitute that, students. ID is 0.4 milliampere. Mu n COX, students, 100 micro. W by L, W is nothing but separately given 32 micro. Divided by 2L, L is 1 micro. Into VGS is unknown. VT equal to 0.7, students. Whole square. Got it now? So this 10 power minus 6 I cancelled out. Okay. So here 100 into 10 power minus 6 becomes what's that? 10 power minus 4. So 10 power minus 4, sir, I can call. Okay. So now I can able to carry that one 10 power minus 4 this side, sir. That becomes a divide means come to the numerator as a 10 power 4. 10 power 4 into 10 power minus 3 become 10, sir. That becomes as a 4. This is 2, sir. 4 2s are 8 you can call. Confirm my option. This is 10 power minus 4 I told. So take this 10 power minus 4 this side, right? Come to the numerator as a 10 power 4. That becomes as a 10. 10 into 0.4 become 4. 4 2s are become 8. Right? So this is nothing but 32, sir. So take this 32 again this side. 8 by 32 becomes 1 by 4, sir. Right? 1 by 4. Finally can go. So 1 by 4 equal to VGS minus 0.7 by whole square. VGS minus 0.7 whole square you can call. Kalpana? Sir, 1 by 4. Make a square root there. That will become 1 by 2. 0.5. VGS minus 0.7. So VGS becomes 1.2 volts, sir. VGS becomes how much, sir? 1.2 volt you can call. Already VG equal to 0 there. VGS equal to VG minus VS. That equal to 1.2 you get, sir. So this is VG minus VS, sir. Sir, already you know that VG equal to 0 there, minus VS equal to 1.2. Implies VS equal to minus 1.2 volts, sir. I got VS now. Therefore, I can calculate RS. RS equal to, from your diagram, VS minus, RS equal to VS minus, right, minus of 2.5 by ID. Here the same current flows ID, you know. VS minus of minus 2.5 by ID you can call. VS minus of minus 2.5 by ID. That is minus 1.2 plus 2.5 by ID, sir. ID is how much there? ID equal to 0.4, sir. ID equal to how much? 0.4, you know. Milli ohms. So 2.5 minus 1.2, sir, that becomes as a 1.3 by 0.4 kilo ohms. That is nothing but 13 by 4, sir. That is nothing but what, sir? 13 by 4, that will look like a 3.25 kilo ohms. First one out. I got RS, sir. Now I can able to go for RD. What is that RD, sir? I told that it is a direct one. So second one I can go RD equal to, there is given RD equal to, this is a 2.5 VD. VD is already given 0.5. 2.5 minus VD by ID. 2.5 minus VD by ID. 2.5 VD is 0.5. ID is how much there? What is the value of ID, sir? That equal to 0.4, you know, into 10 power minus 3. Okay, so that is 2 by 0.4, sir. 2 by 0.4. Take out the numerator, this one, like this. So that is 40 by, so 20 by 4, sir. 20 by 4 become 5 kilo ohms. So RS equal to 3.25, RD equal to 5K, sir. RS and RD respectively can call. RS equal to 3.25 and RD equal to 5 kilo ohms, sir. Option A is the one. Option A is for that one now. Okay, check out the next question now. The slope of ID versus VGS curve of an N-channel MOSFET in linear region is 10 power minus 3 ohm inverse. Okay, at VDS equal to 0.1 volt. For the same device, neglecting lambda effect, what is the slope of square root of ID versus VGS curve in root ampere per volt under saturation is? Sir, what are you asking, sir? First, the slope of ID versus VGS curve of an N-channel MOSFET in linear region is given. So with that data, first I calculate the transconductance parameter, sir. Once I know that, for the same device neglecting lambda effect, what are the value of slope of square root of ID versus VGS in saturation mode, I can able to examine. So I can do this one in 2 steps. First, linear mode I can go. By that I can calculate that unknown of transconductance parameter and come back to the saturation mode of required. By that, what are the slope he asking, that I can able to estimate. Check out now the step 1 now. So what is given, sir? The slope of ID versus VGS, dou ID by dou VGS is given 10 power minus 3 ohm inverse at VDS equal to 0.1 volt you can call in linear region. That is in linear region, sir. In linear region you say. What is the formula of drain current in linear region, sir? ID equal to K dash into VGS minus VT into VDS minus half VDS square ampere. Formula for drain current, sir, in linear region. But I need that dou ID by dou VGS, sir. Dou ID by dou VGS you can call K dash into, so with respect to VGS you can call differentiation of VGS with respect to VGS is 1, sir. Differentiation of VD becomes 0. VDS is a constant. Minus 1 by 2 into differentiation of VDS is 0, sir, because we are doing the differentiation with respect to VGS. So now dou ID by dou VGS is already given. That is, how much is there? 10 power minus 3 you can call. I substitute this one as a 10 power minus 3, sir, equal to K dash into, what you can call, sir? K dash into VDS you say. So already VDS equal to how much there? 0.1 there. So K dash equal to 10 power minus 3 by VDS. So equal to 10 power minus 3 by VDS equal to how much, sir? 0.1. Take to the numerator become 10. That equal to 10 power minus 2 ampere per volt square. K dash equal to what, sir? 10 power minus 2 ampere per volt square you can call. Confirm my option? K dash equal to 10 power minus 2 ampere per volt square, sir. Now I can able to go for what are the condition under saturation mode. Confirm? Step 2 now I can go, sir. In saturation mode, okay, ID equal to K into VGS minus VT whole square. This is the formula. That equal to K dash by 2 into VGS minus VT whole square. K dash is how much? 10 power minus 2 by 2 VGS minus VT whole square. Now you are asking that slope of that square root of ID, sir. Now I calculate square root of ID now. If I do that square root, sir, this is 10 power minus 1. This is what, sir? Root of this one. So if I calculate that square root, sir, square get cancelled. Okay. So this is 10 power minus 1. Root 2 become what, sir? 1 by root 2 means 0.707. That total become 0.0707 VGS minus VT. Now what are you asking? Slope of square root of ID versus VGS, sir. Therefore, dou of root ID by dou of VGS, that equal to 0.0707 into differentiation of that one with respect to VGS, sir. Differentiation of that one with respect to VGS becomes 1. VT differentiation 0. 1 minus 0. That is 0.0707 root ampere per volt. 0.0707 root ampere per volt you may get, sir. Check out the answer for that. So The slope of square root of ID versus VGS curve in root ampere per volt under saturation, sir, 0.0707. 0.0707 you can call. Okay, can I go for next one, sir? For Nmos, given Gm equal to dou ID by dou VGS, transconductance, sir, 0.5 microampere per volt, for VDS equal to 50 millivolt and VGS equal to 2 volt. And GD equal to dou ID by dou VDS, sir, that equal to 8 microampere per volt, for VGS equal to 2 volt and VDS equal to 0 volt, sir. What is the value of threshold voltage VT in volts? He is asking the threshold voltage for that. Check out now what are the data. So this is for Nmos given. Okay, Gm is given dou ID by dou VGS, sir. Dou ID by dou VGS, that is 0.5 microampere per volt for what you can call VDS equal to 50 millivolt and VGS equal to 2 volt. So here VDS less than VGS again. One more option is given and drain conductance are GD equal to dou ID by dou VDS you can call. Dou ID by dou VDS, sir, that equal to 8 microampere per volt. Okay, for VGS should be same 2 volt, but VDS should be 0. So in both of the cases you observe now VDS would be less. So as VDS is small, the body is under linear mode. The body is what, sir? Linear mode you can call. So now I can able to calculate the required one that he asking what, sir? Threshold voltage he asking. Okay. So now in both cases he given VDS is small. It is in linear mode. Under linear mode, what is the formula of drain current, sir? ID equal to K dash into, for Nmos, sir, VGS minus VT into VDS minus of VDS square ampere. So one of that I can substitute, sir. By that I can finally get what, sir? The corresponding what are the thing you want. Suppose I can able to go for GD, sir, drain conductance. Okay, so GD equal to what I do? Dou ID by dou VDS. Any one of that you can substitute, no problem. That equal to K dash with respect to VDS, sir. So VGS minus VT constant, sir. Differences of VDS with respect to VDS is 1, sir. This is minus 2 VDS. Sir, that is nothing but 1 by 2 cancelled out, sorry. So this can get cancelled out. So 2 VDS into 1 by 2 becomes, that is nothing but what, sir, means minus VDS you may get, right. This is that one. There I substitute everything, sir. GD equal to how much? 8 micro. 8 into 10 power minus 6 equal to K dash into VGS minus VT. VGS is how much? 2 minus VT. Okay. So VDS is how much? 0. This one, sir. So finally you may get 8 into 10 power minus 6 equal to K dash into 2 into K dash into 2 minus VT. I keep some equation 1. So if I know that K dash, sir, then automatically I can get that required threshold voltage. So for that I can use one more equation, that is first one there, GM. Now I can able to go for first one, sir. Now GM equal to what I can call? Dou ID by dou VGS. For the same condition I can able to go for, sir. Now GM I can able to go. Now GM equal to dou ID by dou VGS, transconductance, that is drain conductance previous, now it is the transconductance, sir, that equal to K dash into, with respect to VGS means VDS is constant, this is 1, differences from that one VT 0, differences, so VDS is constant, you know, minus 1 by 2 into, because with respect to VGS, sir, VDS is constant, that is 0. Okay, now I substitute that one. GM equal to how much? 0.5 micro. So GM equal to 0.5 micro, sir. 0.5 micro equal to, confirm. So K dash into, this is what sir, VDS you can call, that is already 0. So K dash into VDS sir, K dash into VDS there, K dash into VDS. So what is that K dash now I can able to go? 0.5 into 10 power minus 6 by VDS. So in the first case, what is the drain voltage he given sir? That is 50 millivolt is there. That is given is how much? 50 millivolts sir. 50 into 10 power minus 3. So many ampere per volt square. So if I go for sir 50 into 10 power minus 3 means that you can written as a 0.5 into what you can call sir. So 10 power minus 3 take to the numerator, 10 power minus 3 take to the numerator, become 10 cube. So that becomes as what sir? 0.5 into 10 power minus 3 divided by 50 ampere per volt square. Confirm? Sir, 50 can I write it as nothing but 50, that is nothing but 0.5 into 10 square. So 0.5 cancelled, 10 square take to the numerator become 10 power minus 2, total become 10 power minus 5 ampere per volt square. So finally I can get a transconductance parameter K dash equal to 10 power minus 5 ampere per volt square. So I substituted that in that required condition of this. So from equation 1 I can able to go for that. So from equation 1 I can go sir. Therefore from equation 1 I can come back. So there it is 8 into 10 power minus 6 equal to K dash into 2 minus VT. K dash is 10 power minus 5 into 2 minus VT. Take 10 power minus 5 this side. That is nothing but a divide. That is nothing but 0.8 it comes. 0.8 equal to 2 minus VT. VT equal to 2 minus 0.8. That become 1.2 volt. So threshold voltage VT equal to what sir? 1.2 volt you can get. So this is that value sir. Now I can able to go for the next one of that one students. A Nmos transistor has a VT naught, that is the minimum threshold voltage, you know students. VT naught equal to 0.8 volt. Minimum threshold voltage at which is the source to body voltage 0, you know. Pi B sir, bulk potential you can call. This is called bulk potential, you know sir. Bulk potential equal to 0.35 volt. Okay. And body effect coefficient sir, 0.4 volt power off. Okay. He asking what is the threshold voltage at VSB equal to 3 volt. And VSB equal to much sir 3 volt you can call. So direct formula sir it is, sir bulk potential is given, then I can calculate surface potential, you know. I told that surface potential equal to twice the bulk potential sir. Suppose pi s I written, that is 2 pi b you can call, that is 2 into 0.35 sir, that becomes as a 0.7 volt. Okay. What are you asking sir? Threshold voltage is asking, you know the formula for threshold voltage you discussed from body effect. VT equal to, in terms of minimum threshold voltage, VT dot plus gamma into under root of VSB plus pi s minus under root of pi s. Suppose if VSB is 0, then VT equal to VT naught only I told. Sir, VT naught is equal to 0.8 given, minimum threshold voltage under VSB 0. Body effect coefficient is given 0.4 sir, into under root of VSB plus pi s sir. VSB equal to how much? 3 sir. This is nothing but 0.7 sir. Root of 3.7 it is, minus root of 0.7. So many volts. So if I minimize that one now, that I can able to calculate that threshold voltage sir, that can come down around 1.23 volt. If I calculate that one now, this becomes like this. So observe now, suppose if the body effect sir, if the source to body voltage 0, the channel should be built up just at 0.8 volt. So whenever the source to body voltage is present, so the channel build up should be happen at 1.23 volt. So it require more voltage. So the channel build up become later. So that switching response becomes slow. You can call. That's a drawback. Okay. Check out the next question, sir. For the circuit, modulus of VT equal to volt, K equal to 0.1 milliampere per volt square. Calculate the value of V0 in volts, sir. Calculate the value of V0 in volts. So this is the figure given. I can redraw that. Suppose that I look like a Pmos, sir. This is the Pmos circuit there. This is grounded. This one also grounded. Okay, that is 0.4 milliampere you can call. This is 0.4 milliampere. Okay, and this is the place he asking V0. So that's the place he asking V0, sir. Supply is 5 volt. This is the supply of plus 5 volt. So he is given that modulus of VT, threshold voltage, equal to volt, and K, directly given K, sir, 0.1 milliampere per volt square. He asking that what that V0 there in that circuit. Okay. Now can able to examine that, sir. What is that V0 now? So now let us see this one now. First of all, I can able to examine which mode it is. Okay. See this one now. So gate, this is the source, sir. This is gate. This is a drain. Source, gate, drain. Sir, gate potential is 0, sir. Source potential is equal to what, sir? V0 you can call. Sir, drain potential is also 0 you can call. See this one now. If I compare that gate and your drain potential, sir, VC 0, VD 0 there. VC equal to 0 volt, sir. VD equal to what? 0 volt, sir. Gate potential 0, drain potential 0. And what is that source potential I can able to go? So if I go for VSG, sir, VSG equal to VS minus VZ you can call. That you can call, what do you say, sir? VS means V0 is here. V0 minus 0, that equal to V0. And VSD, sir. VSD equal to what, sir, means? VSD also you see now. VS equal to what? V0. V0. Drain potential 0 again. That equal to V0 only. Okay. Right, as VSG equal to VSD, then VSD must be greater than VSG minus modulus VT. So it is in saturation mode. So I confirm that the body is in saturation, sir. What are the current equation under saturation mode for Pmos, sir? In the Pmos, the equation for current in saturation mode is this one you can call. ID equal to K into VSG minus modulus of VT whole square ampere. Confirm? So I substitute that one now to get that required value of V0, students. So this one now, ID is how much there given? 0.4 milli. K is also given, students, 0.1 milli. VSG calculated, students. VSG equal to V0. Modulus of VT is given, students, 2 whole square. Sir, milli cancel. So this becomes 4. 4 equal to V0 minus 2 whole square. That become 2, sir. So that become 2. That is V0 minus 2. So take V0 this side, sir. So V0 equal to this one you can call. So V0 equal to, if I take this one now, 2 plus 2 becomes what, sir? 4 volt, or 2 minus 2 becomes 0 volt. Confirm? So that maybe the 4 volt or 0 volt, sir. Which one should be right, sir? Suppose if I take V0 equal to 0 volt, sir, what happened there? If I take V0 equal to 0 volt, you can call. See this one now, sir. Vs must be 0 volt, you can call. Vs must be what, sir? 0 volt there. So that's not be possible, sir. Because the current is flowing there. The body is not being cut off mode. So if I keep that one 0, sir, V0 equal to 0 means Vs, this one is a 0. So then what you can call, sir? VSD also 0. So the body is in what, sir, means cut off mode you can call. Not possible, sir. So as Vs not equal to 0 you can call. What you can say that V0 must be equal to what, sir? 4 volt you can call. Okay. Therefore V0 equal to how much? 4 volt. V0 should be equal to what, sir, means 4 volt you can call. V0 equal to 4 volt you say, sir. Because what you can call, sir, 0 volt is not be considered there. 0 volt should not be considered. Right. V0 equal to 4 volt you can find out. Right. That's be the output terminal voltage we may call. So this is the output terminal voltage, sir. If it is 0 volt, if you taken, so all are 0 things potentials means the body current not be allowed. So 0 volt is not allowed, then automatically the answer is what? 4 volt. Okay. Check out the next question now. For the circuit given, K dash equal to 2 milliampere per volt square, Vt equal to 2 volt, calculate V and I. So this is the circuit of 3 transistors are there. So can I draw that circuit, sir? So this is the top one. So this is that connected to 5 volt supply. Here asking I. This is a transistor T3. Here 2 transistors are connected. Okay. T1 it is. T2 it is. So this is the place where you call V. Confirm, sir? These are the transistors. So yes, now this is gate, source, drain, gate, source, drain, gate, source, drain. Sir, for every transistor, gate and drain are shorted, so that every transistor in which VGS equal to VDS and they are in saturation. Okay. So all transistors, so T1, T2, T3, for all transistors, gate and drain are shorted, sir. For all transistors, okay, gate and drain are shorted. That is VGS equal to VDS, sir. So that all are in saturation. All are in saturation, sir. Sir, for T1, I assume that the corresponding current, drain current, I can call Ix here. For T2, I assume that the drain current is some Iy. So you may get that I equal to Ix plus Iy. By that, you can get that value of I. So first, I can come back to the T3 now. For T3 now, I can go, sir. See this one now. For T3, what is that VGS, sir? V is equal to VD, that equal to 5. V is equal to 5, source potential is V. V is equal to 5 volt, source potential equal to common voltage V there. What is that? Vt equal to 2 volt, sir. Vt equal to 2 volt, and already given I, sir, there. I equal to K into VGS minus Vt whole square, you know, that equal to K dash by 2 into VGS minus Vt whole square. Sir, what is that K dash? K dash is 2 milli, sir. 2 into 10 power minus 3 by 2 into VGS 5 minus V, and Vt equal to 2, sir, whole square. So 2 cancelled out. What you can get, sir? 5 minus 2 become 3, you know. 3 minus V whole square milliampere. Some keep equation 1. That's first to T3, sir. Now can I go for T1 now? For T1, I assume that the current is Ix there. Again, use the same condition, sir. Ix equal to, I assume the current is Ix there. Ix equal to same formula I can use, K dash by 2. So first I can indicate what is that VGS for that. So for that one, now we can able to examine VGS, sir. For T1, VGS equal to Vg minus Vs, sir. Vg equal to V, source potential is 0. V, right? So what is that one, sir? Here current I can call Ix, that equal to K dash by 2 into VGS minus Vt whole square. So K dash equal to 2 milli, sir. 2 cancelled out there. Ix equal to 2 into 10 power minus 3 by 2. VGS equal to V, no, and Vt is I think 2 volt there. Vt 2, sir, ampere. So that is 2 cancelled out. What you can get, sir? V minus 2 whole square milliampere. V minus 2 whole square milliampere you can get. So that's one over, sir. I can come back for T3 now, sir, for T2 now. So for T2 also, what is that gate to source voltage, sir? That again becomes V minus 0. That is also same. For T2 now, again VGS equal to VG minus VS. For that also same, VG equal to V, source potential 0, that equal to V volt again. Now what is the current I assume, sir? IY, that equal to K dash by 2 again, VGS minus VT whole square. This is again 2 into 10 power minus 3 by 2. VGS is V, VT is 2 whole square ampere. So this is also what you can get, sir. V minus 2 whole square ampere. So everything I calculated the drain current there. And from this circuit, you know, according to the Kirchhoff law, I equal to Ix plus Iy. I equal to what, sir? Ix plus Iy I can call. Therefore, I equal to Ix plus Iy. What is the value of I you get from the equation 1, sir? So 3 minus V whole square milliampere. Okay, 3 minus V whole square milliampere, sir. This is also milliampere, sorry. So this is milliampere, sir. Just try to get it. So this is also milliampere. Okay. 3 minus V whole square milliampere. Here also milliampere cancelled out. What is this one, sir? Here it is V minus 2 whole square. Okay. So this is also plus V minus 2 whole square. Confirm minus option. Okay. So what I told, sir? So 3 minus V whole square equal to V minus 2 whole square plus V minus 2 whole square, sir. So 3 minus V whole square equal to, so these are the common, that is 2 into V minus 2 whole square. Take a square root, 3 minus V equal to root 2 into V minus 2, sir. So if I minimize that, I may get that corresponding voltage there. What you can call, sir, V equal to 2.414 volt you may get. Check off if you want. You may get that voltage, sir. V equal to 2.414 volt you can call. So once I can get that now, from equation 1, I can able to get that concerned current, sir. So from what is that one he asking, not only V, he also asking I equal to 3 minus V whole square milliampere. So now I can able to go from equation 1. I equal to 3 minus V whole square milliampere. That is 3 minus 2.414 whole square milliampere you can call. Okay. So if I minimize that, now I can able to get that corresponding drain current, sir. 3 minus 2.414 whole square milliampere. That become as 0.34 milliampere, sir. So this comes around 0.34 milliampere. So 2.414 and 0.34 milliampere, sir. Among all these options is given, the correct option is D. 2.414 volt V and corresponding current I equal to 0.34 milliampere. Understand these things, students? Okay. So next class you can able to check out the other topics of that one now. That is nothing but the CMOS logic circuits, all that can able to examine students. Okay. So understood all these things. Thank you. All the best.